range-only SLAM with indistinguishable landmarks. So what is this problem? SLAM means simultaneous localization and mapping. I have one robot here, for instance, in the plane, and this robot is able to see landmarks. So it can be this, or it can be another landmarks, so the red one, or the blue one, or this one. But when they are indistinguishable, it means that all of them have the same color. So it is impossible to make the difference between this landmark and that landmark. Also, another problem is when I have one landmark, for instance, this landmark, the problem we consider is that the landmarks are partially observable. It means when I see a landmark, I am not able to localize it in the frame of my robot. More precisely, it means that I have a subset, for instance, a circle, like this, which tells me, so when I am able to see my landmarks, it means that I am able to guess that it is in this circle. It can be here, or it can be here, or it can be here. I don't know where it can be. So it means that I am not able to localize these landmarks inside the frame of my robot. This is the frame of my robot. So this problem is difficult, and I will explain here using contractor programming how this problem can be solved. So of course, my robot is moving. I know its initial localization. It is able to move inside the space, and it will obey to a differential equation, such as this one. Also, I am able to measure U. For instance, it will be inside this interval or this tube. And when I can see landmarks, I will be able to, for instance, to measure the distance between my robot to the landmark. Okay. So now, the approach to be considered, use contractor programming. I will first explain what is a contractor, which is a basic tool that will be used here and also generalized here. What is a contractor? A contractor is an operator which have the following property. So I will try to explain. Here I have Rn, and I have Rn here also. So what is IRN? IRN is the set of boxes. So this is a box. So a contractor takes a box and returns a box. Now, this box has to satisfy the property. So in fact, I have represented like this, Rn on the left and Rn also on the right. Excuse me, here it's Rn. But in fact, I have to I could also have represented like this. So this box here corresponds also to this box here. So what is important to have a contractor? If I take a box, for instance, here you have X, uh, and here you have C of X. Here also it is C of X. A contractor associated with an equation. So what is a contractor first? If you take a box, you will return a box which is smaller, means that C of x is included in x. Now, if I have an equation, f of x equals 0, it means that no solution will be lost. But it's difficult to represent like this, and I will maybe illustrate on another picture. Here, I take Rn, so I Rn, and I will consider an equation. So for instance, this equation, f of x equal to 0. What is a contractor associated with this equation? I take a box as an input, for instance, this box, and this box is x. And C of x will correspond to such a box like this one. So as we can see, so maybe I will write it here, this is C of x. So all points that were previously inside x are also inside C of x. So it is C of x. Okay, this is when I satisfy these two properties, I will say that I have a contractor for f of x equals 0 for this equation. Okay, so here I have an example. If I consider this equation, so I have an equation which where x1 and x2 are involved. Okay, here it is a representation of the contractor. So what this means? It means that if I have a box, such as this one as input, the contracted boxes will be like this one. So here it is optimal. No, it is not optimal. All of the other boxes are optimal. So what means optimal or minimal? If I have this box as input, it is optimal if I have the smallest one. But I am not allowed to remove a single point. I am not allowed to remove a single point which is inside this curve. So this curve is this one, x2 equal sine of x1. So it is an illustration of a contractor associated with this equation. Okay. So I have also the notion of contractors associated with any set. For instance, if I have a set like this one with a set which is gray here, if I take a box like this one as input, I will not be able to remove a single of these points here. So it means that the optimal contraction here, in this case, will be like this one. Okay, so I am allowed to remove this point, but not this one. So I'm not only allowed to define contractor with respect to equation, but to any kind of sets. So a contractor is said to be monotonic if it satisfies these properties. It means that if I increase a box, then the contracted box will also increase with respect to the inclusion. It will be important if I apply the constructor twice, and it is the same as if I apply it only once. Okay. Now I have the contractor algebra, which makes me possible to handle equation. So if I have an equation, if I have a set, I can associate a contractor. So if I want to manipulate this equation of this set, I will do it through contractors. So I can intersect contractors, make the union of contractors, make the composition, apply it several times, and so on. So it is what we call contractor algebra, which makes me possible to manipulate sets or equation in a guaranteed way. I can also define contractors with respect to any kind of information. For instance, if I have a database and a map, for instance, and I have some information, such as, for instance, one robot is inside the water. So I can define also contractor for that. For instance, a representation is given here. I have some boxes here. So each of these boxes corresponds to, for instance, this one corresponds to X. What is a contracted box if I know that my robot is inside the water? So I take this box and I will contract like this one. So I remove all this part. Because, so this is C of X. Because I know that my robot is inside the water. So here it will be this. Here, if I contract it, so here I remove this. Here I remove everything. So it means that in this case, C of X is equal to the empty set. Here I have some water, so the contracted box will be like this one. Here, excuse me. This is false. Excuse me. C of X, in this case, C of X equal to X. So nothing is removed. In this case, there is no water. So in this case, everything is removed. So C of X, in this case, equal to the empty set. Not in that case. Okay. Now this is false. Because it can be everywhere inside this box. How we can build contractors when I have equation? So the idea is simple. I can use interval arithmetic for this. For instance, if I consider this equation, if I want to contract x1, I will only write x1 equal to x3 minus x2, which implies that the interval for x1, will be replaced by the previous interval for x1 because I know initial a prior interval for x1, but also will belong to x3 minus x2. And here I use interval arithmetic to compute this. And if I perform this statement, I will contract x1. I can do also the same for x2. For instance, I know that x2 is equal to x3 minus x1, which implies the following contraction: x2 equal to x2 intersected with x3 minus x1. Also here, x3 equal x1 plus x2, which yields the following contraction: x3 intersected with x1 plus x2. Okay, so this corresponds to a contractor. It is the contractor associated with this equation. Just what I have explained now. So now if I have some equations, some information and so on, I will be able to combine them using what we call fixed point method or interval propagation. I will explain now. Assume that I want to solve this system. So in this system, you have two equations with two unknowns, x and y, and I want to solve it. So what I will do, I will first use interval arithmetic to build a contractor for this one, and then I will build a contractor for the second equation. I will start with a box, and I will call the first contractor, so let's say C1, and the second contractor, C2, and I will repeat it until I have no more contraction. So I will illustrate now. The two contractors are given here, and we can see that at this step, here, here, or here, I use interval arithmetic. So it is important to remember that I have initially some equation, and I will transform these equations into contractors. And then I will not manipulate anymore this equation, but only the contractors. This is what I will do. This is my two equations. Okay, so I have here my initial box. So this is x, for instance. I will call it x, and I will consider these two equations. So I will contract with respect to the first equation. And if I do this, I will contract like this. So this one corresponds to the first equation, so I have applied C1. It means that I have removed all this part here. All this part has been removed. Okay, I will not draw everything, but everything here has been removed. Then I have my second contractor, say C2, and we can understand that now my new box is this box, and I will call C2. If I call C2, it means that I will, if I have the optimal contractor, I will contract with respect to this, like this, because I am not allowed to remove a single of this point here. Okay, so if you prefer, I have removed all that. Okay, that is what? And then I will apply C1 once more. And C2 and C1. Okay. Then at this step, I get a fixed point. It means that I'm not able to contract this box. Okay. So what I do usually in this kind of situation, of course, my two solutions are here and here. So I have to separate this solution and I have to bisect. So I can bisect here either like this or like this. I will obtain two boxes. Okay. So here I decide to bisect like this, and I will contract with respect to the first one and to the second one. But at this step, contractors are corresponds to polynomial algorithm. When I bisect, I will become exponent. The complexity will become exponential with respect to the number of variables. So in a contractor programming approach, I have to avoid as much as possible all bisections. Okay, I bisect, I contract, and I converge to these two solutions. Here I will try to generalize the contractor approach explained in the previous slides. So what do I need to define a contractor? I need a set. So this set here is denoted epsilon. I need also a partial order relation, this one. Uh, and I need also two operators. So the join and the meet. The first one corresponds to the least upper bound, and the second one is the greatest lower bound. So in this case of situation, I will be able to define intervals. I have some kind of, if I take a discrete lattice, often you will use what we call the as diagram, as direct, to represent uh, a lattice. So I will try to represent one here. So I will have the top element and here the bottom element, top bottom. And most of the time we can take this kind of example of lattice. So it is a specific lattice, a discrete lattice. Okay, so all my elements are the nodes here, 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 and so on. Okay, this is the top element. I will say that this element is smaller than this green, okay, because we can compare them, and so I will explain. If I take two elements, for instance, this one and this one, I cannot compare them, but I can say that the green element here is larger than this element because I can go from this one to the other one, going down like this one. But I can say that this element is smaller than the red one because I can go to it going down. But I cannot compare this element and this element. Okay. But if I take uh, these two elements, I can define the least upper bound. So if I take this element and this element, the least upper bound is this point, because this point is larger than this one and larger than this one, and this is the smallest one because this one is also larger than this element and this element. but it is not the smallest one. So if you want the top element is larger than all other elements, and the bottom is smaller than all other elements. So what is an interval inside this? An interval, I will try to take two elements, for instance, this one and this one, and so it will correspond to A and B. So A is an element of epsilon. B is an element of epsilon. But what is an interval? What means A and B? A and B corresponds to all, it is a subset like this, and it will correspond to, can represent like this also. So it contains a number of nodes. Of course, only the nodes belong to this interval. So here I have 12 elements. A and B corresponds to all x in epsilon such that A smaller than B, excuse me, smaller than B. Okay, so in fact, if I have lattices, I can define intervals for this. It is a definition of interval inside the lattice. A subset of the lattice is said to be an interval if it can be written, this subset can be written like this. It means it corresponds to all elements that it encloses all elements that are larger than the lower bound of this subset and smaller than its upper bound. When you have intervals, it is important to note that the empty set and epsilon itself are interval of epsilon because they correspond to this definition. So the whole lattice epsilon is an interval. Epsilon, if you want, it is the interval top, bottom. Is this interval. Now I can define, of course, interval R of R because R is a lattice, but I can also define other type of interval. So I will try to represent like this. I will consider here trajectories. I will consider the red trajectory, the orange trajectory, and the green trajectory. The red trajectory will be called A, the green B, and the orange will be called C. It is a lattice. I can say, for instance, that B is larger than C. I can say also that A is larger than C. Okay. Now I cannot compare A and B, but I can define, for instance, with this color, the sup of A and B. It will correspond to the, so here it will be T for us. So the sup is here like this. Okay. And now I can also define the mean of A and B. So it will correspond to uh, this. Okay. Now I can also observe that A sub and B, E and C corresponds to A. A, B corresponds to C, corresponds to C, and so on. So the set of trajectory is a lattice, and we can define interval of trajectory, and we call it tubes. A tube is an interval of trajectory. In the machine, we'll use a specific way to represent tubes because we have to use floating point number. And here you have an illustration like this. So this is an illustration of a machine tube. Okay. So this, okay, so this one is a tube, and here you have a trajectory. It is also the same for subsets of R. So it is on the right. So I will represent two sets, A like this, uh, B like this, and another set. Okay, I will take the green one. C. So of course, the set of subset of Rn, so here Rn, with the inclusion is a lattice. I can say, for instance, that A is smaller than C. I can say that B is smaller than C. But I cannot compare A and B. Cannot compare them. But I can define the smallest subset, which is which include A and B. It will be the union. So the union, of course, corresponds here to this. And I can also define the intersection as the smallest subset, which is included in A and B. So it will correspond here to that. Okay. So I can also define interval of subsets. And here you have an illustration of a set X. Here in black, you have a set which we can call this set X minus, which can be represented inside the machine also. And here, this set will correspond to X plus. So enclose everybody. So what we can say is that X in this situation belongs to the interval X minus. x plus. Okay, if here I have f plus and here f minus, I can say that f here belongs to f minus f plus. So in this kind of situation, I will be able to use contractors. So to use contractors, I will have to define the notion of CSP, which classical in the constraint community. So what is a CSP? To have a CSP, I need variables x1, xn, which are the unknowns of the problem. So x1 can be a set, can be a trajectory, can be a point. It is the variables of my problem, the unknown. I have some constraint. For instance, type of constraints can be if I have set, the set A is included inside the set B. It is a constraint. The trajectory f is always positive, or it is a odd function. It can be constraint, can be unreal. For instance, it can be A plus B equal to C. Okay. And now my variables, I have some prior information, and I know that x1 belongs to x1. So it is a set which encloses my variable. What I ask here is that my domains should belong to lattice. Variables could also belong to lattice. It's better because if they belong to lattice, then I will be able to ask my domains to be intervals. But it is not always the case. So I can have some variables that do not belong to lattice and I can still use contractors. But it is important to have the domains which belong to lattice. Okay. So now, if I have a lattice, I can define intervals. So if I have a lattice, let's say L1, another lattice L2, inside the first lattice, I can define an interval. So take care, this one can correspond to, for instance, to a set, A minus, this one to A plus, it can correspond to a set. Here it can be trajectories, whatever. But I can define L1, the cross product, Cartesian product between L1 and L2 is also a lattice. So I can say that this point is smaller than this one, means that it will be each component will be smaller than the other one. So if this corresponds to a box inside this Cartesian product. So it's what we call here an hyperdomain. It is hyperbox if you want. Hyperbox. Okay. Here I have the representation of what we could have as contractor. For instance, here I have a lattice, Rn. I have the subset of Rn, so it is another lattice. And inside the machine, we have some kind of discretization because the machine is already discrete, which is represented by all these bars. It means that we have a finite representation for the element I want to manipulate. If I take an interval here, for instance, this interval, and here another interval, and I have here a constraint which involves x here and a here. Uh, this is a representation of this constraint. I have a box, an hyperbox for this hyperbox here. And what corresponds contractor here, it, with respect to this contract, means a contraction represented here, which contract the previous hyperbox, this one, into this hyperbox, this one, without removing a single solution. So I remove all that, but I do not remove a single solution. Okay. So I will now consider some example, and the first example will be graph interval. A graph, a set of graphs is a lattice. So I will first consider a graph. I have nodes inside this graph, and I have some arrows, like this. Arrows, 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 arrows. The nodes are these elements. So I will say that a graph is smaller than another one if I have more arcs. It means that if I add some arcs, then I increase the graph. For instance, if I add this one, my graph will be bigger. So this one, I increase the graph at the moment. Okay, and so what corresponds to top element? The top element corresponds to the graph like this. So this is the top element. What means, and I have to add also this to have the top element. Okay. Okay, this is the top element. What corresponds to the bottom element? The bottom element is the graph with no arcs. So it is a lattice. I will be able to define intervals of graphs. To understand this, I consider this graph. So it has several arcs here, and if I have a graph with three nodes, A1, A2, and A3, I can associate a matrix. For instance, this arrow here corresponds to the one here, because here I have A1, which is in relation with A1. I have also this corresponds to the fact that A1 is in relation with A2. So here I have A2, A2. So because of this, I also have this. Okay, so now this corresponds to that, and this arrow corresponds to this element. This one corresponds to so this I will call J is this one. J minus is this one. J plus is this one. So it is clear that I can go from J1 to J plus by adding arrows. So this J1 is smaller than J2. I can associate to each interval of graph an interval of Boolean matrix. For instance, if I have, since I have, so this element corresponds to a relation between A1 and A1. Since here I have no relation, no arc, and here I have an arc, I put here 0, 1. Now, why 1 here? Because I have one row from A1, A2 to A1 here and also here. So it is sure I have 1 because it is the same on the left and the right element. Now, why 0 here? Because between A1 and A2, I have no relation here. Excuse me. A1 and A3, I have no relation here for J minus and also for J plus. So it means that I have 0 here. So now, what means, for instance, a contractor in this situation? Assume that I know that the graph is symmetric. For instance, if I know it is symmetric, it means that if I have an arrow in one direction, I will have an arrow in another direction. Then I will be able to contract this element to 1, and because of the 1 which is here, and this one, I can contract it into 0. So this contraction comes from the fact that I know about the symmetry. If I know the symmetry, it is a constraint, then I will have the corresponding contractor. Now assume that I know that the graph is reflexive. Means that each element is in relation with itself. So it means that I will be able to contract this one to 1, this one to 1, and this one to 1. Okay. So it is a case I know that it is reflexive. And if I know some other relation like the transitivity and so on, I will be able to have a new information with better contraction. Okay. So it is illustrated here. Assume that I want to build the minimal contractor with the constraints, which tells me that I have an equivalence relation, which means equivalence means reflexive, symmetric, and transitive. Then I will be able to perform this contraction. So of course, I was not able to contract this and this element of the initial interval graph, but I was able to contract some of them, like this one, and so on. All information will correspond to contractors. Now, set intervals. Set intervals, as previously explained, the definition is if I have an uncertain set, as it will be the case in robotics, this is the uncertain set here. To represent it inside the machine or to take into account the uncertainty, I will be able to enclose it between A minus, so A minus is this set, the gray set, and A plus corresponds to all this. Okay. It is what we call a set interval. The, the subset of Rn corresponds to a lattice. So the bottom element is the empty set. The top element is the set of all vectors of Rn. It corresponds to Rn itself. If I have two sets, A minus, so it is A minus corresponds to a set. So A minus. Here in this representation, abstract representation, A minus corresponds to a point, but in fact it is a set. A plus is larger, so it corresponds, it encloses it. A plus. A plus. Uh, so all elements here, element here, corresponds to, for instance, A, one point here. But the set of all sets that are inside, between the two of them, so here I have represented three of them, it corresponds to the interval A minus, A plus. So since the part of Rn is a lattice, I can define the interval of subsets of Rn. In the machine, I represent using the notion of subpavings. So this is a subpaving, also quad trees, the literature, quad trees, or oak trees. So here it's for R2, here it's for R3, or K trees for RK. Okay, so it's very efficient to represent using this notion to represent inside the machine. Okay, so as previously explained, all singletons are intervals. The smallest of them of set intervals is the empty set. This set interval encloses all subset of Rn. Okay, so since it is a lattice, I can define, if I have two sets A and B, the smallest of the least upper bound is this. Largest lower bound is that. Okay, so it is the enveloping box of A and B. So it is the smallest interval which encloses A and B. It is this. This corresponds to the smallest box which encloses the set A and B. As it was the case for intervals, I can define an arithmetic on set intervals, and it is only illustrated in this slide as follows. Here I have a set A minus, so A minus, A minus is this, is black. A minus is this. A plus is all this. Okay, so here it's A plus. So we have an uncertain set A, which is between, let's say it can be like this. I don't know exactly how it is, but it encloses the black box and it does not intersect the gray boxes. Okay, so now assume that I know, oh, excuse me, assume that I know that A is inside this and B is inside this. So here it corresponds to A and this one corresponds to B. Now I can I can define some operation such that the difference A and B or B and A as illustrated here. So I will now explain how this can be done. So if I have a set, let's say A, and a set B, the difference, what I call difference between A and B, correspond to this. Okay. This difference corresponds to the intersection between A and the complementary set of B. Now assume that I know that A is uncertain and belongs to this interval, n minus A plus. B also is uncertain, belongs to B minus B plus. Then, if I use the same principle as interval arithmetic, I know that A, B belongs to the interval A minus B plus bar, A plus with the difference between B minus bar. And the order is not the same for A, so here, because this operation is increasing with A. It means that if I increase A, this set will be larger. But it is decreasing with respect to B. It means if I increase B, the difference will be smaller. So because of this, I have to put plus here and minus here. Okay. So this corresponds to the operation A difference than B. The same principle as classical interval arithmetic. If I apply this operation, I am able to define here it is a representation of A difference with B, and here it will be the difference between B, difference between A. I can also make the union of these two sets. And this, since union is monotonic, it suffices to take the union of the lower bound and the upper bound. So this corresponds to that. And here I have the union between A and B, and so on. And since there is two different ways to to since difference between A and B union the difference between B and A is equal to this union between A and B and difference between A intersected by B. So it is a classical property of set theory. It is not surprising to have this which corresponds to that. Okay. Okay. It was just to illustrate the possibility to have an arithmetic to manipulate interval of subsets of Rn. Now I will define the contractor, associated contractors. I have here interval of subset of Rn, here also, and I have some relation between two uncertain sets A and B. For instance, this may correspond to A included to B. It is a constraint, and I have all pairs of A and B which do not satisfy the constraint, and all pairs of A and B that satisfy the constraint. Now, in the machine, I take a hyperbox, like this one, and I will contract, as previously explained, without removing a single point which satisfies the constraint. So, if I take, for instance, this constraint, A is included in B. I have two sets A and B, and I know that A is included in B. I also know that A belongs to A minus A plus, and B belongs to B minus B plus. So how can I build the contractor for this? First, I rewrite A included B by as follows. A is included in B is equivalent to say that A is equal to A intersected with B, which implies that the contractor for this, since there is no multi-occurrence of A, I know that the optimal contractor will be the following. A is equal to A intersected with A intersected with B. So it's not exactly the same intersection. I will try to explain it as follows. When I define, when I know that A belongs to this, so because of this, I know that A intersected with B belongs to A minus intersected by B minus and A plus intersected with B plus. The only reason is that this operation is increasing with respect to the two arguments, A and B. So it is an extension, intersection extension, and I write it like this. And minus intersected, A intersected with B. And it corresponds to this operation. Okay. Now, if I have I will also show a representation for this. I have here a box for A and a box for B. So this is A and this is B. And when I write this, I am here in the lattice of the subset of Rn. It means that here I have empty set, and here I have Rn, the largest element. So when I write this, it corresponds to this box. So this box corresponds to A intersected with B. Oops, excuse me. Excuse me. This box corresponds uh, to A intersected with B. So now, what means the difference between, what means this operation? So it corresponds to an intersection in a classical set theoretical sense inside the subset of Rn. It means that, again, I will represent the same lattice of the subset of Rn, and assume that I have a set A, and I know that this set belongs to this interval, but it also belongs to this interval. Okay, so this one will be called, for instance, A, and this one corresponds to B. So I know that A belongs to A, and I know also that A belongs to B. So of course, what can I say? I can conclude that A belongs to this. And I will write A belongs to A intersected with B like this. But as we can see here, it is not the same intersection. The previous one corresponds to the blue one here corresponds to this intersection, whereas the green one corresponds to this intersection. Not the same meaning. So we have explained, we have this formula for the contraction of B for A, and for the contraction of B, it is exactly the same principle, except that we have written A included in B as follows: B equal to A union B, and we obtain this formula. We can also build the contractors for more complex constraints, such as this constraint, and we obtain the following contractor. With some representation, graphical representation, I have three intervals for A, B, and C, which are uncertain set. And here I have the corresponding contraction with respect to the fact that, uh, as previously said, A intersected with B equal to C. And now I will deal with some application about the SLAM, of course. Uh, Before explaining the SLAM, I will explain a simple example involving an uncertain set, which is X. So we know that X is included in A, defined here. I know A. I know B. I know that X is included in B, in A, B is included in X. I know that it does not intersect C. So I will build a contractor for this one, a contractor for this one also. And I know that the image of X is by a function f is X itself. So what is f? F is a rotation with an angle minus p divided by 6. We will apply a contractor for each constraint up to a fixed point. Here A is almost known, that's why the frontier, the y frontier is very small. The same for B and for C. So this one corresponds to A, this one corresponds to B, and this one to C. So each of them is almost known. Now I take the first constraint, which tells me that X is included in A. Remember that I want to find X. X is included in A, included in this set. So it means that uh, uh, I know after that X will not intersect this gray part, but I have no, at the moment, some information about the no inner approximation for X. That's why here I have the white region, which is large. So the white part corresponds to some uncertainty. Okay, so I know that these points are not inside inside X, but I have no information corresponding to the white part. Okay, so now I consider this constraint. I know that B, which is here, is included in X. So it means that all points here are inside X. So now I will have a better information for X, where here I have X minus, and this will correspond to X plus. But in the previous image, this was possible for X. This was not possible for X. Now, so this was possible for X, but now this is possible for X, but it is not possible for X. Okay, so I know that this is possible for X. This is not possible for X. I have to be between the two of them. Okay, now I have another constraint will tell me that it does not intersect C. C is here. So it means that X now should be like this, should enclose the black part, but should not intersect the gray part. Now, if I rotate it, I will have to, it should correspond to X. So in fact, I will rotate the, I will rotate the interval for X, and I will intersect with the previous one, and I will obtain this. And I will obtain, I will contract this, this constraint, or I will contract using the contractor associated with this constraint up to the fixed point, and I obtain this. So it means that for X, X could be like this, for instance. It encloses the gray part, can go like this, come back here. It could be like this. Whoops. With all inside corresponds. So a possible set is like the green one. Now I will come back to my initial problem, a slam with undistinguishable marks. I have one robot, which is described by some state equation. I know that u by my input, which depends of time, so this trajectory belongs to a tube u. So if you want, I have a tube like this. This is u of t. And I also have some marks, but the marks are uncertain. So at the beginning, I will only know that the marks, m of 1, for instance, uh, belongs to a box which corresponds to minus infinity plus infinity. If I am in R2, of course it will be minus infinity, so square and square. Okay. Again, I am indistinguishable for the marks. I will need to represent the correspondences by a graph. So the SLAM problem is a chicken egg problem of cardinality 3. So what that means? It means that if I know the map and the association, and I am able to localize myself using a localization method. So it's not so difficult. It's nonlinear state estimation problem, not so easy, but it can be considered as we have tools for this. If the trajectory of the robot is known and the association between marks are known, I will be able to localize my landmarks. It is a mapping problem. It is not so difficult also. I can solve the problem. And again, if the trajectory is known and if the map is known, then the correspondence between landmark is known. It can be done quite easily. So in fact, each of the three problems can be solved using existing methods. Now, the main problem is to solve the three all together. To solve this one, I need to have solved the two other. sub-problems. This is why we call it a chicken and egg problem. And of calling it is three because we have three sub-problems. So what are these unknown variables? We have the marks. When I have my robot, which is here, I don't know the trajectory of the robot. I know its initial condition, but not the trajectory. The marks. So I have one mark here, one mark here. I don't know where they are. I may have some boxes for them, but the boxes are huge initially. I have another variable which corresponds to the free space. So what means the free space? The free space is a space where you have no landmarks. It means that in this situation, the free space will correspond to everywhere except where I have the landmarks. So here and here. So okay. So it will be important. It's a variable I want, a set variable I want to characterize also. And what is the data association? When my robot is able to detect a landmark, for instance, at time t1, it is able to detect this landmark at time t1. At time t2, my robot is here, it is able to detect one landmark. Is it this one? I don't know. Detect another landmark. So, in fact, I want to say that at time t3, it has detected landmark 2, but at time t1, t2, it has detected landmark m1. So what I want just to say as information is at each time I have a detection. So for instance, I will have the first detection, which corresponds to t1, a detection t2, a detection time t3. So I have some kind of nodes of the graph. And because here and here it is the same, I will associate this detection at time t1 and the detection at time t2. Like this and like this. And again, at time t3 is the same at time. I will do this. So the graph I am representing here, it is an unknown graph, which is called J. For the association graph, assume, for instance, that at time t1, my robot detects a landmark. So this is a landmark. Let's say M1. Now, assume also that later, at time t2, the robot detects a landmark also. Is it the same as the previous one? It means that is the detection at time t1 corresponds to the detection at time t2. If it is true, then I will have an arc between the node t1 and t2. How can I be sure that it is the same? So of course, if there is some differences, I can only by the exteroceptive measurement to see the differences. But when it corresponds exactly, I cannot be sure. So I have to introduce the tool for this. And in this example, I take here, the landmarks are different. So the typical situation is this one. And okay, it is represented here. So to understand how it works, when I do a detection, I will have to introduce the concept of sector. So what is a sector? A sector is a set of the workspace which enclose one and only one landmark. For instance, this is a sector. This is also a sector. This is not a sector because this set encloses two landmarks. So any set which encloses a unique landmark is a sector. The green one is not a sector because it does not include a single landmark. So a sector is a subset of the workspace which contains a single mark. In our example, we have one landmark here, and we have two sectors. Indeed, the first sector here contains a single landmark, and this one also is a second sector. So in fact, if I have two sectors, one included into another, then I know that the difference between the two, so here, for instance, this part, the difference between two sectors associated with the same mark does not contain any landmark. Here also, I have a situation where I have two sectors. Here, I have represented four sectors. The first one, the second one, and due to the special configuration of the four sectors, I will be able to be sure that this landmark does not correspond to this one. Okay, this is a way I will be able to associate my landmarks. So for our SLAM problem, we have among the unknowns, I will represent by a state equation. This is a state equation. And I will have a number of detection. So to each detection, I am able to associate a sector. Of course, some Ti may be equal to Tg, for instance. It may happen. So we'll see why it is important. So all the Ti are not all different. Of course, I assume a tube for U. And I assume also that each sector contains a unique mark. So we have an egocentric representation. It means that the sector depends on X, on the state of the robot at time Ti. So it is an example of a sector. For instance, X corresponds to the position of the robot. And if I have this set, the set of all A which satisfy this distance equation, this set depends on X and it corresponds to a sector. So it is important to remember that if the state of the robot is X, then the sector, which is represented here, is centered on the robot, so depend on X. So consider here an example. I have one landmark here and one landmark here. So this robot send, for instance, with a sonar, send ultrasonic wave, and it has an echo. If the echo is clear, then it will see that inside this ring there is a single mark. So I represent like this, where I have AG, which corresponds to all, so all this part. So I will this one corresponds to all the disk. And I have also another sector, which is this one, which corresponds only to that. So, so since HI is included in HJ, I can conclude that they correspond to the same mark, because this one contains a single mark and this one also. So I can conclude that inside the white part, there is no landmarks. I can also define the free space as the set of all points of the plane which do not correspond to a mark. So if I have some sectors H1, Hm, and if we denote by this quantity the mark associated in H1, which is unique, then I can conclude that if I have this inclusion, I can match the two detections. If they do not intersect, then I know that they are different. If they are included one to another, I know that the difference between the two is included inside the free space because there is no mark inside. So I consider here just a small representation. I have different sectors. I have, for instance, I know that H2 encloses a single landmark, also for H3. So I can conclude that in this, I have the same mark. So inside the blue set, I have a single mark. Now, so it is represented here. The blue part is represented here. Inside, I have a single mark. It is also the same here. So I can conclude that inside this set, I have a single mark, but inside this set, inside H5, I have also a single mark. So the single mark inside H5 is here. So since H5 contains a single mark, I can conclude that here I cannot have any mark. Otherwise, I would have two marks inside H5. It means since since H4 encloses a single mark, it is necessary here. Okay, so I know that inside the blue set, I have a single mark. Also, here inside the pink set, a single mark. I can also conclude that inside these areas, I have no marks. I have no marks here. But here, I may have a mark. Okay. I know I have a mark here. I may have a mark, but maybe the mark inside H6 could be here, but could be here also. It depends of the other mark. For instance, if I know that it is here, I will know that I have a mark inside this part. But here, I don't know if I have a mark here or not. Okay. Oh, well, I cannot conclude anything about this. Maybe it contains 0 or 1 mark, no more. So about the association graph, I have some my detection, A1, AM. and I will be able to have an arc between the node A1 and AG if they correspond to the same arc. Now I will try to show that my SLAM problem is a constraint satisfaction problem. So in fact, the unknown, or X, corresponds to the position of the mark associated with the if detection. I will have also the sector, which is unknown. So it belongs to an interval, which may correspond, for instance, to empty set Rn at the initialization. The free space, the same. It is unknown at the beginning. It does not contain any mark. And the association graph. So all variables are here, and the corresponding domains are here. So this is an interval. It is also an interval. It is an interval. It is an interval. This one is not an interval. It is a set which does not correspond to an interval. But remember that what is important, of course, interval is good to represent domains, but it is not mandatory. What is mandatory is to have a lattice structure for the domains. So intervals corresponds as a lattice structure, but the set of subset of Rn has also a lattice structure. So about the initialization of my domains. The trajectory, I don't know it. So it will be minus infinity plus infinity over n. Over n. Okay. The initial condition is known to be equal to 0. About the detection, I don't know where they are. They correspond to R2. Okay. About the sectors, it will be between empty set. And so as I know at the beginning that Hi is included in R2, so it will be between empty set and R2. The same for the free space and the graph. It will be between the graph with no arc, so it corresponds, this one corresponds to the top, and to the bottom, it means the graph with arcs everywhere. What about my constraint? My constraint, I will have my state equation, the fact that my sector corresponds to, I have an expression for my sector, and this expression depends on the state of the robot. Here I know that each detection belongs to the sector. I know also that if the A of I is equal to A of j, then I have an arc, so it is one of the variables of the graph. I know also that if AI belongs to the J sector, then I will have this. Also, I know that if I have an arc between nodes I and j, then the difference between the two of them will correspond to the free space. And I know also that each detection does not belong to the free space. So I have 7 variables, 7 constraints. Each of them is associated to one contractor. This one will, I will be able to contract each of the variables by using each of the contractor associated with each of the constraints. So it is what we call here a constraint graph. The unknown variable are x. Here the detection, the graph, and the free space. Each of the variables are linked by some constraints. This is one constraint which relate to unknowns, the sectors and the trajectory. The trajectory is, of course, satisfies an equation. So it will be a relation, this one, between x and x, and so on. So it is a graph relation. So it is the graph of the constraints of my problems, which can be represented as this. Okay. So now I will consider a test case. So I consider 10 marks, like this. In an environment. I have also a robot, and it is able to measure some distances, like this one. It's a rangefinder. So of course, when you measure a distance, it is not able to know where the mark is. It is here, but it may be anywhere inside a circle. Inside a circle around the robot. The robot is described by some state equation, and the set-valued sectors function are given by this expression. So I will consider a sector just to say that one of the mark in this side, this interval, so the distance is inside this interval, but also another one to say that between the robot and the first echo, there is nothing. So I represent by two sectors. Of course, I will have an inclusion between this sector, which is included inside the second one. So I will apply all contractors one after another, and I will obtain here, at the first step, the trajectory by integrating the differential inclusion using interval methods, interval integration. And on the right, I have the graph. So the right column corresponds to the association graph. And here on the left, I have the trajectory. So at the beginning, the trajectory is poor, but after I can reconstruct using by calling the contractors up to a fixed point, I will be able to control, to have a better and better approximation until I get the fixed point. So here on the left, I have the fixed point for my trajectory, and here I have the fixed point for my association graph. This can be obtained in a few minutes. This result could be obtained in a few minutes. Of course, at the beginning, when I integrate my trajectory, I know my initial condition, and what I have here is that when I integrate, I obtain a trajectory which becomes less and less accurate. But when I call my contractors, the trajectory becomes smaller and smaller, and we can see that at the end, I can control the width, so W is the width of the tube. So I can control the accuracy of my trajectory. So at the end of this example, I was able to detect some association, not all of them, but between the detection. And here is represented the free space. So I know that the inside the white zone, it corresponds to F minus. F minus is included in the free space. So I was able to reconstruct the trajectory, my landmarks, the association graph, and also the free space.